Hello and welcome back to Paleocast. My name is Dave Marshall and this is episode 99 on Megalodon and marine megafauna, in which Liz interviews Dr. Catalina Pimiento of Swansea University. Undoubtedly, Megalodon is the world's most famous extinct shark, and in this episode we hear everything we know about this taxon, its ecology, and how it got to be so big. Its ultimate extinction is also considered not in isolation, but placed in the wider context of the entire marine ecosystem. In regular Paleocast news, we're just about to hit our 100th episode, and we've arranged an interview with one of the biggest names in paleontology, someone we've had many requests for in the past. So keep your eyes out for that coming out very soon. In that episode, we'll also have an entirely new sound and we'll be introducing some new faces to the team. So very exciting times ahead. As for this episode, please keep on liking and sharing on social media. Reviews on iTunes and Facebook will always be appreciated, and let us know what you thought in the comments section. We hope you enjoy this interview.
Hi Catalina, thanks for speaking with me today.
Thank you.
Can you maybe start off by telling me a bit about yourself and how you got to where you are today?
Yeah, I've always been interested in sharks, and actually I decided to study biology because I liked sharks since the beginning. And that was because when I was 15, in Latin America, the 15th birthday is a big deal for a girl.
Yeah.
But my dad gave me a subscription to National Geographic for my 15th birthday, and the first issue of that subscription had a great white in the cover, and I remember just reading this magazine like if it was a book, from cover to cover, as opposed to just what you do with the magazine. But I read the whole thing, and the article about the great white was about how it's vulnerable and threatened with extinction, but we don't know much about it and things like that. And that day, just being in my room, I decided I want to become a biologist and I want to study sharks. Back then it was more like, I'm going to save sharks. But then it transformed into, I'm just going to be a biologist and study sharks and see how it goes.
Yeah. So you're now a fellow at Swansea University.
Yeah.
How did you kind of get to that position? Where did you study before and do your other research?
Yeah, I studied biology in Bogota, and then I did actually my thesis, like we call the thesis, but it will be, I guess, senior project year or something like that. I did it in Mexico on whale sharks. And then I went to Panama as an intern to the Smithsonian Tropical Research Institute. And I worked there for a while on whale sharks because that's what I was kind of already working on. But then the expansion of the Panama Canal started, and then there was a lot of digging to expand the Panama Canal. And with that, a lot of fossils were exposed. And the Smithsonian had some sort of contract where they will rescue the fossils. And a lot of shark teeth appear in this collection, and I was the shark person at the time around, and they started bringing me all these fossil teeth. I never thought I was going to be working with fossils in my life ever. Interesting. And then all these fossils came to me, and I started identifying them, and the question of why a lot of these species are around today, if they're, these fossils are from 20 or 10 million years ago. I thought it was really cool, interesting that they were the kind of same species, or at least in terms of the teeth, they were the same. So I started becoming more interested in paleontology, and then I met my, who was my graduate supervisor, Bruce McFadden, who was doing a lot of projects with Panama, and he was a paleontologist that works on the neotropics, but also mainly terrestrial mammals. Nothing to do with sharks, but he was very interested in Panama and on the fossils of the neotropics, so I started doing a master's with him in the University of Florida on Megalodon, which was the biggest shark that we found in Panama. And then the PhD, as well with him in Florida, where I try to understand everything possible about this one species.
Yeah.
And then after that, I got a fellowship to do a postdoc in Zurich.
Yeah.
For a year and a half, and then I got a Humboldt fellowship, and I did a 1-year postdoc in Berlin.
Mm-hmm.
And after that, I got the Marie Curie fellowship to do this new Megafauna project in Swansea.
So that's cool. I guess, a lot of paleontologists you talk to are like, I always wanted to be a paleontologist. I always wanted to work on dinosaurs. So you went at it totally from biology and then sort of stumbled into fossil sharks.
Absolutely. Like I thought my life was going to be all about swimming with sharks, not collecting teeth. But so it was a surprise, but I'm very glad it happened.
Yeah. So I guess you kind of mentioned, obviously, your PhD and master's, you worked on Megalodon. Yeah. So I think that's maybe where we can start talking. I think Megalodon doesn't really need a massive introduction for most people. I think most of our listeners will know, but can you say kind of from your point of view why Megalodon is so interesting and kind of summarize what Megalodon is?
Right. Yeah, well, like the size is the obvious thing, right? This is huge. You find it a lot. I'm not very good in the field. Like, I'm sorry with the ones that love being in the field, but for some reason I struggle with finding small teeth because I guess I also came from a marine biology background, and for me field work was more based on the idea of swimming with sharks. And then when I started collecting, I did struggle a lot finding fossils, and a lot of people around me in Panama were finding tons and tons of teeth, and I was next to them, I just wouldn't see them. But Megalodon, of course, I will see because the teeth are huge. But beyond the obvious thing, which is big and it's easy to find, it was because it's an apex predator, right?
Yeah.
And because I come from a marine biology background, I did learn very early in my studies that apex predators are very important for ecosystems. And once you lose them, you have these cascading effects that have negative consequences for the communities or the structure of the communities, and it cascades down to the lower levels. So I thought that if Megalodon was an apex predator, then that extinction may have had very important consequences for communities at large back then. So I think that was I became so interested in this particular species. It's large, it's cosmopolitan, and it became extinct. Yeah. So we can learn a lot from it, because what we know about current removal of apex predators is based on extirpations or declines, but not really on extinctions, because fortunately any apex predator has gone extinct yet. Yeah. We still have our great white sharks, we have the orcas. Yeah. So if we wanted to learn what really happens when a global species goes extinct forever, then we have to look at the fossil record, and that kind of made sense for me at the time becoming a paleontologist, because if I wanted to save sharks and if I wanted to understand their extinctions somehow, I needed to look at the fossil record. So it was like a logical kind of step. What do we know about this species? Well, we know it was the largest shark that ever lived.
How big?
18 meters. I calculated the biggest. Wow. Although it could be argued that was a bit too much and it could have been 16, but still massive.
Huge.
We know it lived in all the oceans of the world. Okay. And we know that, what else? That it may have eaten mammals. Yeah. I mean, that makes sense, such a big animal. But the things that we discovered during my PhD were also very basic questions, like when it became extinct, how did that happen, and why? Yeah. And that's like the main obsession that I had during those years. It was trying to understand those questions.
So how long did Megalodon live for?
So it lived from 23 to the early Miocene. Yeah. And it became extinct in the Pliocene. Okay. So
sorry.
Go ahead.
I was just going to say, is that like a very kind of abrupt extinction, or do you see it kind of peter out? Or
actually it happened globally. I thought one of the hypotheses I wanted to test is if the extinction happened gradually in terms of distribution. If it was, like becoming extinct in some places and then some other places. So we did this study that was published in the Journal of Biogeography a few years ago, where we mapped all the distribution of Megalodon through time. And we see how the distribution has been basically the same in terms of the range until it suddenly became extinct. But the most important thing about that study wasn't the fact that it didn't change in distribution, but it was that we did a niche modeling. and we found that temperature didn't correlate with the distribution of these species, because it was argued that temperature had something to do with the extinction of these species, meaning that in the Pleistocene, when the oceans were getting colder, then this animal had to go extinct. But we found that actually temperature, or sea temperature, didn't affect where Megalodon will live. So we rule out temperature as a direct driver of extinction. And in turn, we found that the evolution of competitors, like for example, the modern gray white, but also the decline of potential prey, were more associated, more related with the decline. So more than these climatic factors, we claim that instead of environmental factors, biotic factors had to do with it. But that was a story when I was obsessed with this species. But quickly enough, I realized that I needed to include more species, more like a community level kind of understanding if I wanted to know what happened to the species, because obviously Megalodon was not alone and it was interacting with species. And that's where the marine megafauna project that I did in Swansea came up.
I guess I didn't realize that like the great white actually overlapped with Megalodon.
Oh yeah,
So
it did overlap, but for the last millions of years. But the thing is that it's very hard to say when exactly a species becomes extinct and when exactly another evolves, and that's something that we have tried to deal with the fossil record. But fortunately, there are many cool methods now that we can assess, and we calculated that the extinction of Megalodon was at the end of the Pliocene and close to the Pleistocene boundary. But of course, that's based on many records, and to know exactly when it happened is tricky. We have a pretty good understanding of it, but I think that was a bit not the subject we were talking about.
I think it's just interesting. I just didn't realize that they overlapped at all. I kind of always had it in my head that
one Megalodon,
or that just it went extinct and then a different thing evolved, not that they actually overlapped. So that's interesting. I guess the other thing, shark fossils, obviously we think of always as teeth. Is there anything known from Megalodon other than teeth, or do we just have those huge teeth?
Yeah, mainly the teeth, but there's also, as far as I know, one specimen of a vertebral column that is in Belgium.
Yeah.
And so it's a fairly complete set of vertebral centrum that we have. But they're not very common. But they are very valuable because this centrum have these concentric rings where you can track many other things like stable isotopes through time and stuff. So it's a very interesting resource.
No, it's you always hear about teeth, and I know that the shark fossil record is not great other than teeth. There's tons of teeth, but then everything else is not as good.
Right.
So that's interesting. But I guess you can learn quite a lot from just the teeth in terms of looking at different sort of ecology and things about its lifestyle. So what other things have you been able to look at with Megalodon just from the teeth?
Just from the teeth, we actually found that they could use shallow waters as nurseries, and that's what actually the first paper I ever published, and the first on Megalodon, obviously.
Cool.
And that was because in Panama we were finding teeth, but the teeth for Megalodon were smaller than the ones that you used to.
Yeah.
So we hypothesized that it was because it was a nursery and those small teeth were baby sharks. So we run a series of analyses, very, very simple ones, in which we just basically calculated the total length of each individual. And we found that most of them were juveniles. Yeah. And based on what we know from modern sharks, we know that nursery areas are typical habitats where you find juveniles that are shallow water and they're very productive. And those are the characteristics of the place where we found these teeth. So we know that based on the teeth that they use nursery areas. And nowadays we know they're essential habitats for shark survival, and then we kind of showed how sharks have been using them for at least millions of years. Yeah. So that was something cool. The study that I mentioned about the distribution was also based on only teeth. Yeah. In that study, it was kind of a meta-analysis in the sense that we collected all records, all papers ever published on this species, and we mapped the occurrences. What else? Well, we estimated the most likely time of extinction based on occurrences that were based on teeth.
Yeah. So just in terms of teeth, when you talk about things like nursery and looking at the ages, are the teeth so different from everything else that a small tooth, is not just a species of a different shark?
For the case of Megalodon, yes.
Yeah.
That's the case. For other species like, a bull shark or, a Caribbean shark, you don't know really to the species level. You can basically just say up to genus.
Okay.
But with Megalodon teeth, it's very straightforward. They have a very diagnostic shape and size and geometry or other key characteristics that are easy to identify. Yeah.
Huh. That's interesting. I guess as we said before, the size is the big thing that you always think about with Megalodon. So I always just think of like a big tooth. But then if you have something that's smaller,
because you see all these big teeth that are as big as your hand, right?
Yeah.
And in Panama, we're finding the same shape, but just half of the size, or like the size of one of your fingers instead of your whole hand. And but then it could have been argued at the time that then it wasn't because they were smaller Megalodon, but that they were in the back part of the jaw,
earlier,
because they have smaller teeth in the back of the jaw and bigger teeth. But the shape also changes. So if it's a very straight and symmetrical tooth, then it has to be from the front of the jaw. If it's bended towards one side or the other, then it's more likely to be from the back. So those kinds of things, we had to learn a lot about this based on jaws from the great white, for example, how the shape has changes, and actually to calculate the total length, you have an equation for each tooth position. So it's not that you take a tooth and then you apply one equation. You have to take a tooth and then know where exactly, or at least where in general, it is within the jaw, and then apply that position. So for a paper that we did on body size, which was a very fun paper to do, because we travel to the most important museums around the world to find Megalodon teeth, so that's pretty cool.
Yeah.
So we went to Lima, to Buenos Aires, to London, to Berlin, to all these amazing places where you have collections, and we measured teeth and we calculated the total length to see if there were any patterns or changes in body size through time for this species.
Yeah.
And that's because it was proposed that, or it has been shown that this species was part of chronospecies that was increasing in size through time, in which the ancestors of Megalodon were smaller, and Megalodon reached the larger size. So we did this analysis and we found that within Megalodon, within the species, there were not changes in size through time. So it was like stasis. It didn't change. So we were trying to test the hypothesis of increasing in size being some sort of driver of extinction, like maybe Megalodon was increasing in size through time until it couldn't get bigger and become extinct, but we didn't find that. So for each tooth that we got from the museums for that study, we had to know where in the jaw it would be to apply the equation. So a lot of times I wouldn't know exactly, but I will know that is a lateral tooth. So then I will use the equation for each lateral position and then average the size.
So it's closely enough related to modern species like the great white that you can do that with some sort of
mostly
trust.
Mostly it's because the great white is the only relative that is similar to those tooth. So even though they're not directly related, that's the best modern analog we have.
Okay. Oh, that's interesting. And going back to the question about the nurseries, is that still the only place that we've seen that for, like, the Megalodon or even other sharks in the fossil record, that site you found in Panama, or are there other examples of that?
There are other examples. Actually, after that study, some others were published on different species, and even from older time periods. Papers where they have found actually the egg cases and things like that.
Cool.
So based on that, more than the presence of juveniles, so more direct evidence. So nurseries have been found for a few species, which is pretty cool.
That's impressive that the egg cases even have been fossilized, given how little we know from shark fossils in general. And then you get an egg case. Yeah, that's really cool. I guess obviously we talked about Megalodon most definitely being extinct.
Absolutely.
Despite what other people may say. So in terms of why it became extinct, you've kind of alluded to the different things. So what was the sort of final suggestion that you had in your paper, your final, like, this is why it went extinct?
It's interesting how we come up with the final kind of suggestion. And like I said, our biogeography paper was saying, okay, temperature was not the cause. Some biotic factors like competitors or prey may have been. Could have been the evolution of the gray white or the decline of some mammals. They would. But this all became clear when we did the Megafauna, the Pliocene marine Megafauna extinction, because first we have already proposed that Megalodon became extinct in about 2.6 million years ago, so at the end of the Pliocene, beginning of the Pleistocene. But then we used more robust analysis to actually calculate the time of extinction and origination of all the marine Megafauna. But most importantly, the extinction rates through time. And we found that higher extinction rates took place in the Pliocene. So, and specifically in the late Pliocene. Of course, we found that extinction rates were going up since the late Miocene and also were high in the Pleistocene. But we call this the Pliocene marine Megafauna extinction because most of the extinctions took place in the Pliocene. Whether or not Megalodon became extinct in the late Pliocene or a particular species became extinct in the Pliocene or in the early Miocene, in the late Miocene or the Pleistocene, I mean, that's irrelevant at this point. I mean, we know that around that time there was an extinction event. And I think some species become extinct at some point and some others after. But at that point, then we knew that a lot of species become extinct at that time. We knew temperature had nothing to do with the extinction of Megalodon directly. So then we assessed sea level. Because sea level at that time was changing a lot. But what we didn't know was whether or not sea level was affecting area available for this animal. So we found that the extinction rates were higher in the Pliocene, and then we found out that around the time the area availability for marine Megafauna decreased significantly from the from the Pliocene to the Pleistocene, and that marine Megafauna, including Megalodon, had much less area available during the Pleistocene. So the reason why I say that this became clear about Megalodon extinction with this paper is because what I think happened was that Megalodon became extinct during this marine Megafauna extinction, probably at the end of the Pliocene, beginning of the Pleistocene, but probably at that point the prey for Megalodon maybe would have gone extinct earlier and was declining, right? And then the area also become smaller and smaller because area was decreasing. So the prey was declining, the Megalodon wouldn't have enough space to find more prey anyway. So it was climatic in the sense that it was sea level changes, but it was area and then it was the prey. So it's it's very hard to pinpoint one particular factor because everything is happening at the same time together and in a long time periods as well. So it's hard to pinpoint to what exactly and when. But we have a very good understanding of the fact that Megalodon became extinct as part of the marine Megafauna extinction during the Pliocene, probably at the end of the Pliocene, and that sea level changes that cause area loss and the decline of their potential prey and the rise of competitors took place.
So you're kind of getting this area that is much smaller. You still have the same number of animals, smaller area, but then they have no prey, and so they can't like go around and find new prey, and you still have animals competing for fewer resources. And so you're gonna have this whole big
all things
problem.
coming up.
That's really interesting.
I don't know which will happen first. Maybe area, because one of the things we found is that area declined massively at the end of the Pliocene. So let's say that with the area loss, some species become extinct. And maybe Megalodon may have gone extinct because those species declined in the first place, or they decline, other competitors appear, less area, climatic oscillations with sea level, all of this combined. It's a global species. You have to kind of see the big picture to understand, as opposed to just a few fossils in a particular place.
No, that's interesting. I guess I haven't really thought about it in terms of a global species, because normally when you think of extinction, it's, they're fairly restricted to, maybe they're on one continent or they're in one ocean or something. But to have something that goes extinct from the entire world all at the same time
is interesting, because you have to keep this global aspect in, this large scale aspect in your head when you're thinking about these global extinctions, right? And at the same time, when you look at things like that, then they have to be very coarse, they have to be very broad. You can't go into little details of when exactly, or what particular, because it's just a big thing going on in a lot of time, like the period of time that this took place is large. Globally, cosmopolitan species, massive. So that's where everything became clear when we looked at it as a megafauna, because that brings more relevance to the story.
So I guess the other question then, thinking of like big giant sharks, you have also today we have like whale sharks, which are completely different from Megalodon. Did these kind of animals ever overlap or something similar to that? And how does, the ocean today has now giant things like a whale shark, but
not giant.
Megalodon. So how can you
actually
talk about that a bit?
We addressed that question recently in our evolution paper, and how do you become so large? What do you have to do? If you're a shark and you're swimming in the sea and you're like, I want to be big, what do I have to do? That was like the main question we wanted to ask in this paper. And we found that there are two strategies for giantism, or two pathways. One is mesothermy, which is being able to control your body temperature, at least at some degree. So, for example, the temperature of your brain, your eyes, your stomach. That's mesothermic, so not entire endothermy, or becoming a filter feeder. So then in those two pathways, you have two iconic extreme size sharks, which is Megalodon in the mesothermic and predatory, and then the whale shark in the filter feeding. The whale shark is here and the Megalodon is not. But what we found is that for the first strategy, the mesothermic strategy, to be supported, in this, coming back to the marine megafauna paper, you have to have a lot of area available, because these mesothermic animals, relative to the ectothermic animals, need a lot of area to find a lot of prey to maintain their high metabolic demands.
Okay.
So this pathway is going to support giant sharks only if there's enough area available.
Okay.
And there's no an extreme size mesotherm, because the area was reduced in the Pleistocene, so it was no longer supported. Whereas for the whale shark, that didn't really affect it, because plankton is more available than large prey, and then they were able to find it. But that said, I wouldn't say that the whale shark is completely safe of extinction, because microplastics, for example, are threatening filter feeders nowadays, also to extinction. So these two pathways can be vulnerable, maybe the mesothermic more than the filter feeder, but they're both, in a way, it's a trade-off, you become large, but you also have to pay a price.
And I guess in general, I think large animals have that problem of being more likely to go extinct, regardless of your kind of how you're living and what you're doing. They're just more sort of susceptible to that extinction.
I think Megalodon was really big, and it needed to eat a lot, so area is lost, prey are scarce, then was.
Were there any filter feeding sharks that overlapped with Megalodon, or?
The two strategies have cohabited, but one thing that doesn't overlap is in a single individual. So a single species, I think, cannot be mesothermic and filter feeder at the same time. That said, it has been proposed that some filter feeder race can be mesothermic.
Interesting.
However, the reason I don't think this is the case is because all the studies that have done on mesothermy have shown how this strategy has the evolutionary advantage of enhanced predation. So the reason why animals become mesothermic, or one of the advantages of becoming mesothermic, is being able to hunt more efficiently, because your speed to hunt is more effective when you're able to warm your own muscles of certain parts. So I don't see how a filter feeder will benefit from, except for being large. So that's another thing, being mesothermic, because you're large, and then you somehow your body temperature is stabilized.
Yeah. I had to think about that.
Great. It wasn't just me. But if you have mesothermic in this, as a gray white does or a mako shark does, which is these red muscles, currents of, I don't know the specifics of the physiology, but is effectively to enhance your predation. So that's what I don't think these filter feeders are properly mesothermic in the same sense. Maybe it's a different way of mesothermy. But as far as I'm concerned, there are these two strategies that don't overlap in a single individual. So you have these separate pathways towards giantism, and actually we found that the two strategies are significantly different from everything else. So there's a relationship between what you eat and how large you get in sharks and in fish in general. But if you are any of these two strategies, mesothermic or filter feeder, you deviate from that relationship.
How easy is it to tell from the fossil record if something is mesothermic?
Very hard. That was actually the main weakness of our evolution paper, was the fact that we had to infer this thermoregulatory capability from sharks. Nevertheless, there has been some papers published where they suggested that the Megalodon lineage was mesothermic, and they looked at the stable isotopes from the teeth, and they compared that with the temperature or the other conditions from where the from where the tooth were collected, and the temperature was different, in the sense saying that they were not changing, didn't have the sea temperature. Also, a lot of closely related clades close to Megalodon are mesothermic, like the lamnid sharks, for example, the gray white, and the mako shark. So it kind of makes sense. Of course, we repeated our analysis without the fossils, and then we got different results. So it's open to further results, and it will be great to kind of find a way to know the thermoregulatory capabilities of fossils in general. Like if you can look at it and find some sort of proxy for it, then we should rerun everything and look at it. But at least we kind of have a better idea, know how to be giant and the things. But I think this can change rapidly if we find more fossils or more techniques to better understand their strategies.
And I guess it's difficult to know, if you take the fossils out, you get a different answer, but is that because you've interpreted the fossils incorrectly, or because the fossils give you a different answer?
Or because the fossils have that unique information.
And so they're giving you something else. So you can't, it's hard to know which one without any more evidence. I guess kind of leading on to what you're doing now, so you've kind of shifted away from looking at the sort of giant sharks, and you're looking a bit more into sort of conservation and like looking forward rather than looking back. So how can you use the stuff you've learned about gigantism and sort of marine megafauna in the fossil record to what's happening right now in the oceans?
That has been something that I feel like going back to my basic desire of
back to your roots.
Exactly. I always wanted to do that, like kind of translating these lessons to the present and the future. Well, one of the things is that the way we calculate extinction rates in the past could be potentially extrapolated to the future. You use the same result, the same methods, but the other way around. But the new project that I'm working on, we're actually just basing our probabilities of extinction on IUCN status. So each species has an IUCN status that could be endangered, vulnerable, critically endangered, or could be least concern. So playing with these probabilities, we have been trying to predict what's going to happen in the next 20, 50, 100 years with marine megafauna, and then assess the ecosystem consequences in a very broad kind of way, right? Because what point ecosystem is going to be, but based on in the premise that marine megafauna is vulnerable, it has gone through an extinction event not long ago, geologically speaking, and now is again being threatened to extinction. So to what degree we're going to be losing functions or like functional diversity or at least richness based on the future. And it's still very preliminary, but it's a very depressing story because so many of our current big, enigmatic, charismatic, and amazing animals are likely to go extinct in the near future. And we're not only going to be losing species, but we're going to be losing all the services and the functions that they do in the ecosystem. So a whale goes extinct, and then we're losing the fact that they're transporting nutrients across ocean basins, that they are providing a lot of organic matter to the oceans. They're transporting nutrients, they're moving around, there a lot of species depend on them. So it's a lot of all these things that we're going to lose as well. And because we found that they're very unique actually in terms of those functions. There are very few functions that are played by more than one species. So it's a very sad story really to look at the future. Like, when you look at the past, at least you don't get depressed about your results.
Yeah, no, I understand that. I can't remember exactly what it was, but I saw a kind of documentary or something a while ago that basically, a single, say, blue whale dies in the ocean, and how important that is to, hundreds of thousands of other animals who use it for food or to for their houses and all of these things, and you don't really think about that. So it's not just about the blue whale going extinct, but that trophic web of how much it affects everything.
It goes extinct with everything associated with it.
I guess this is kind of maybe a bit of an abstract question, but just thinking about megafauna, what in the ocean today, where do you draw the line of what's considered a megafauna and what's not?
I'm just thinking of funny thing somebody said, that if megafauna was 10,000 faunas, like a megabyte. No, actually recently was defined as everything that is beyond 45 kilograms.
Okay.
So for the marine megafauna, the current marine megafauna project, we have whales, we have pinnipeds, we have sea turtles, we have penguins, we have sharks, of course, and some big fish, but we also have the giant clam or this giant squid. We also have so it's cool because it's beyond taxonomy. Sometimes we get so focus on a particular, I've been obsessed myself with a single species. So, I had to learn a lot about marine mammals and sea turtles, and, it gives you a completely different perspective of how to understand extinctions, because like we just said, nothing goes extinct alone, right? And it's likely that once you lose one species, other species go extinct. Just look at the Megalodon example that I was giving. It's likely that some of their prey may have gone extinct first, and then they get extinct. So it's everything is interacting. And
I guess that's something that, as paleontologists, we don't really think about it. And I think it's good to start looking at what we can learn from the past and how to look at in the future. And I say that as somebody who works on pterosaurs that have nothing to do with anything in the future. But I think that this is a really kind of nice way of making paleontology more relevant to a lot of the things that we're asking today, and how to look at things like modern extinction of the oceans.
Well, we have more extinctions in the fossil record than we have today. So, if you want to understand extinctions, you have to start by looking at the fossil record anyway. So, most of life has already gone extinct. So we need to look at it in order to understand it. But I think it's also important to keep in mind that we're going through a very different kind of extinction, right? It's human driven. It's a lot of things are happening much faster than happened in the past. So of course we need the fossil record to understand it, but we also have to be conscious about the fact that this is different. The species are facing different pressures. So we have to just make sure that when we do those comparisons, we can, we make it with that in mind.
Much like when you said, the difference between Megalodon and a whale shark. Megalodon went extinct as a mesotherm, but the whale shark has microplastics, which she didn't have to deal with in the past. So,
there you go, exactly.
That's really interesting. Well, I think that's Great.
Okay,
so
great.
Thank you very much, Catalina.
Thank you for inviting me.
Paleocast was brought to you by Dave Marshall, with Joe Keating, Laura Soul, Liz Martin-Silverstone and Caitlin Colery. It was made possible by funding from the Paleontological Society and the Paleontological Association, but the show now relies on contributions from you, the listeners. If you've liked this episode, please consider donating, and thanks to everyone that's helped out so far. We'd also like to thank the Ocean Collective for use of their music. Please visit paleocast.com for the supplementary material to this episode and for our archive of past programmes. Subscribe to our Twitter feed @Paleocast and like us at facebook.com/Paleocast to get all the latest news.